upgraded my OS to Big Sur, the next Mac OS. And now all of a sudden, like, the computer is treating me like I've never used the computer before. And so absolutely every application I have, like Teams this morning was a bit of a, like, it would say like, you need to give permission to use your microphone. It's like, okay, grant permission. It's like, we need to restart Teams. It's like, and then you get back into Teams and it would be, we need permission to use your camera. It's like, and then it did it again to get permission to share my screen. So hopefully now everything is clear and makes sense. And hopefully it doesn't ask me this every time. And then it remembers my answers. So welcome everybody. We are back into unit whatever number on phase equilibria. And we started this last class and we got partway through. We had an assignment that was due last night, which was the bonus assignment. And we have another one that will be posted sometime today based on the beginnings of this unit. I might sprinkle a couple of electrochem questions in there too, just in case you didn't get enough electrochem from our previous unit. But anyway, I think that would be probably a good idea to give you a bit more practice on that. We have a quiz starting next week, and I'll sometime, I'm not going to make promises there. When I have it ready, I'll send you an email and let you know when that opens up. We've been talking at the end of last class about phase diagrams, and have a picture of a phase diagram here on my screen for some bogacium. It's not a real thing, of course. Some hypothetical material, and it's asking a couple of questions about that. So it's giving this 760 torr, which is equal to 1 atmosphere, which is the defined pressure at which, when the vapor pressure of a substance equals that, then that would be its boiling point. And we picked 1 atmosphere instead of 1 bar, even though they're similar to each other. We've switched over to almost everything for bar except for vapor pressure defining boiling point. So the first question says, does bogosium have a lower or higher density in the solid phase versus the liquid phase? And this is a question that you can look at based on this line right here, because what this diagram is showing is that low temperature and high pressure, we're looking at the solid phase. In this phase here, we're looking at liquid. And over here, low pressure, high temperature, looking at a gas phase. And we have this E, which we call the critical point, where over in this area, we say we have a supercritical fluid. And the supercritical fluid is kind of, as we said last class, an intermediate state between a gas and a liquid. You can think of it as, you know, clusters of particles. So it's a liquid-like within a cluster, but these clusters are separated from other clusters like a gas. So it's got properties like a liquid where it can dissolve things very well, but also like a gas where it can flow very easily, it can expand to fill its container, and it can do things like that. So this is asking us for the solid to liquid transition. So what we can see is this line here, which is indicating the point at which you have an equilibrium between a solid and a liquid. If you cross that line, it means you're changing a phase from solid to liquid or liquid to solid. So the way we can tell if the solid has a lower or higher density is if you pick a point, say like right here in the liquid phase, and you apply pressure. If you can apply pressure to a liquid and compress it into a solid, we know the solid must be more dense. So at this point, we have our liquid, we're going to apply pressure. When we increase pressure, we go vertically up. And you can see if you go vertically up from that point, you're going to cross from the liquid into the solid phase. So that tells us that if we can compress a liquid into a solid, the solid has to be higher density. Okay, so yes, the solid phase of this substance must have a higher density than the liquid phase. And this is actually the case for almost every substance, except for a few notable ones. Water, of course, we talked about last class as being the other way around. So if you have a solid that is lower density than the liquid, that would have a solid liquid line which goes to the left of the vertical line starting at A. Explain the phase changes that occur as you go from point C to point D. So we're starting in the solid phase, and we are increasing the temperature such that we have a phase change at this point, and we go well into the gas phase. So we're going directly from a solid to a gas, and going directly from a solid to a gas is sublimation. So in that case, you don't go through a liquid phase at all. If you wanted to go from a solid to a liquid to a gas, you could start up here maybe and go this way, increasing temperature. Then you would see the usual solid melting into a liquid first at this point, and then evaporating into a gas at that point. What point represents the critical point? The critical point is B, above which temperatures and pressures above that, we have supercritical fluid. And the other point, which is not defined yet here, is A. A is what we call the triple point. And it's the only temperature and pressure where you have an equilibrium between the solid, the liquid, and the gas phases all at once. Great. For solids, actually, that phase diagram has 3 phases, solid, liquid, gas, and I guess 4 if you count supercritical fluid. You can have more phases than that. And we had already talked about for a solid how you can have polymorphs of a solid, where a polymorph is different crystal structures of the same chemical compound. Allotropes is another word that we use if that chemical compound we're looking at is not a compound at all, but is in fact a pure element. So here we have 2 different stable forms of sulfur. We have rhombic and monoclinic. And we have a phase diagram for sulfur right here, where we have the solid phase, we have the liquid phase up here, and we have the vapor or the gas phase over here. But notice that there's 2 solid phases. There's the rhombic solid phase and the monoclinic solid phase. So if you had, let's say you're at a point here, and you're in the monoclinic phase, which looks like this, and you applied pressure, what would happen is you would cross a phase barrier and you would move into the rhombic phase. So you could pressurize the monoclinic form of sulfur and convert it to the rhombic form. Now, the problem with this is that solid to solid transitions are famously slow. So it's not like you can, take a crystal of monoclinic, apply pressure to it in an anvil or something like that, and then in 10 minutes you have the new form. Sometimes these changes take millions of years, and these are the sorts of changes that that people in geology concern themselves with. So, for example, they can tell which temperatures and pressures different solid forms are stable in because they know the temperatures and pressures at which those substances are found underground. And then they can figure out, well, okay, this is whenever the pressure is this and temperature is this, it's always found in this form. And whenever the pressure is higher or lower temp, it's always found in the other form. So this is just to show what a phase diagram looks like when you have more than one allotrope, or in this case, or polymorph in the case where you have a compound. This is just showing a picture of actually the monoclinic sulfur crystals. They can be formed through deposition, which is the reverse of sublimation. And this is a place in New Zealand where there's volcanic activity, and sulfur at very high temperatures comes up from underground. And you can see all the yellow that you see there. And it can actually, when it's in the gas phase, deposit out as crystals, like you can see right here in a cave. If you've ever been to New Zealand, not New Zealand, obviously it's why it's on my mind here, Vancouver, there is close to, if you go around, there's a park called Stanley Park in Vancouver, and there's a kind of like a active trail, I guess you could call it. It's like a paved road that goes all the way around the outside of Stanley Park. And what do they call that trail now? Anyway, you can't drive on it, but it's just for biking and that kind of stuff. And there's beaches all the way along. And there's one point, if you're on that road and you look across the harbor, you can see a great big pile of sulfur, bright yellow pile. And it's a huge pile. Like, you know, if you're a person standing there, it's like, you know, tiny, tiny, tiny little person compared to the size of this pile. And this is all sulfur that was extracted from natural gas in Alberta. And what they do is they refine the natural gas, remove the sulfur, reduce it down to solid yellow sulfur, like you see in this picture, and then they put it on ships and ship it over to China. And it's used to make sulfuric acid over there. It can be oxidized. And it's also used in the process of vulcanization, which is a process used to treat rubber to make it much more durable. So anyway, if you see that big yellow pile ever in Vancouver, you know what the cause of that is. So phase diagram for water. Water, you know, this is the kind of the part of the phase diagram we normally concern ourselves with because that's the conditions under which we normally encounter water. But it's actually known that if you put water under a huge amount of pressure, there's a number of different crystal forms that it can take. And there's different names for it. You can see there's ice 2, ice 3, ice 4, ice 5. That all exist under different conditions of temperature and pressure. So this is probably, you know, this is thousands of bars. These aren't conditions that we would normally encounter ice in. Although, I don't know, maybe like ice at the bottom of a glacier. I don't know what the pressure is like under those conditions, but maybe you have different forms of ice too. These are all polymorphs because ice is, or water is not a pure element. And there's actually a work of science fiction by Kurt Vonnegut. If you ever read any Kurt Vonnegut, which book is that? I forget, one of his early ones, but he talks about a hypothetical form of ice called Ice 9. And do you remember the story I told last class about that drug that the drug company made, that once this new crystal form was found, that's all they could get from that point on. Did I hit record? Yeah, we're recording. Good. A little panic attack there. Yeah, so it's true. Sometimes you can have a crystal form of a substance that's very, very stable, but it won't form because it's very slow kinetically to form. But once you do form it, it becomes the dominant form at that point on, if there's any amount of that material around. So in this science fiction book, the concept is someone somehow makes a crystal form of ice called Ice 9, which has a melting point above 0 degrees Celsius. And so if you touch that crystal to any body of water that's liquid, it'll instantly turn into this new crystal form, which is a solid. So the worry is that if you put some in the ocean, the whole ocean would just crystallize into this new form, which would have a melting point much higher than actual water. And the only reason it doesn't do that spontaneously is because that crystal form had never been exposed to ocean water before. I don't think we have to worry about that as a, you know, real world problem, but interesting concept all the same. So yeah, in geology, these are 3 different crystal forms of this particular material, Al2SiO5, and it goes by the names kyanite, andaluzite, and sillimanite. And these all are most stable at specific conditions of pressures and temperatures. And if you look at the pressures we're dealing with here, this is gigapascals, very, very high pressures. And I guess you could have a point right here where you have an equilibrium between all 3. So there you go. So this is water. We talked about water as being weird because this line, which is the solid liquid phase boundary, skews off to the left as opposed to off to the right, like almost everything else. So just a few notable points here. One is if you go to 1 atmosphere of pressure and you move over to where we have the gas liquid phase boundary, and you go down from there, that temperature will be the boiling point of that liquid. Also, if you stop at the solid-liquid boundary at 1 atmosphere, that's going to be your melting temperature, which is 273 K. The triple point here is D, 273.2 K, so just slightly warmer, and pretty low pressure, 0.006 atmospheres. If you increase the pressure here to 2 atmospheres, which this scale is kind of wonky, you know, 0.006, 1, and then 374. So I don't know, let's say it's like, I don't know, up here somewhere is 2. And if you were to go over from 2 atmospheres, notice the boiling temperature, the temperature at which the liquid converts to the gas, it's going to be at a higher temperature here than the normal boiling point. So by putting it under pressure, you increase the temperature at which it boils. So going to 2 atmospheres will actually increase the boiling point to 394 Kelvin. So that's an increase of 21 degrees just by going up by 1 atmosphere. And this is the whole concept behind how a pressure cooker works. Is that by putting food into a pressure cooker and then sealing the thing, and you heat it, that creates an increase in pressure on the inside up to around 2 atmospheres. And there's a little pressure release rocker at the top to keep it from going too much higher than that. That'll increase the boiling point of water inside at 121 degrees Celsius. And that 20-degree increase in temperature actually has a significant effect on the rate of cooking, the rate of the chemical reactions inside. And actually, there's a field of chemistry which involves putting chemicals that you want to do a reaction with into a pressurized vessel, into a pressurized reactor, and conducting the reactions under high pressure, because that allows the boiling temperature of the liquid inside to go much higher and therefore increase the rate of reaction by quite a bit. You got to be careful though, because chemical reaction inside a pressurized container, if the container fails, you have an explosion on your hands. So it doesn't always make the most sense. The boiling point of water, if you reduce the pressure, like if you come down here somewhere, that will reduce the boiling temperature of water. And it turns out that at the top of Mount Everest, the pressure is, atmospheric pressure is about 0.3 atmospheres. That gives you a boiling point of water around 69 degrees Celsius. So if you go up in elevation, it actually can take a lot longer to cook something. And the unit that I've often seen used is how long it takes to boil an egg. And I think it's if you're at atmospheric pressure, to boil an egg, hard boiled, takes about 10 minutes. And so if you went up a mountain and you boiled an egg, you would need longer than 10 minutes because you don't have as hot a temperature. And I don't know if you could put eggs in a pressure cooker, but if you did, I mean, I don't see why you couldn't. It would take a lot less than 10 minutes. There we go. So hopefully by now we do know what a solution is. A solution is a homogeneous mixture, meaning there's only one phase, and it involves at least 2 different substances dissolved in each other. Solutions can be solids, which is a kind of a weird thing to think about, but if you have an alloy between 2 different metals, you can think of it as like a solid dissolved in a solid. And even though nothing's moving around, it's like, you know, obviously it's a solid, we still consider that to be a solution. So brass, pretty well every alloy we would consider to be a solution. We have liquids, obviously. Liquids are the most common solutions we think of, where you can have one liquid dissolved in another, like you would have in like vodka, say, ethanol and water. Or you could have a solid dissolved in a liquid as well. You can also have gases dissolved in each other, like air is a mixture of primarily nitrogen and oxygen mixed with each other. And yeah, those are all examples of solutions. So when we have a solution, we always consider there to be what we call a major component and a minor component. And we give the major component the name solvent and the minor component the name solute. which is interesting. And when we say major component, in most cases that's obvious, which is major and which is minor. Although you could imagine in like two gases, if you had like 50% oxygen, 50% nitrogen, which one is the solvent and which one's the solute? I can tell you this much. In my 20 or so years of practicing chemistry, I've never seen a situation where that confusion between which was the solvent and which was the solute came up. So hopefully you all can be chemists and embark on your chemistry career and never have to worry about the edge cases where it may not be abundantly clear which is the solute and which is the solvent. One interesting thing is that sugar is extremely soluble in water. You can dissolve about 2 kilograms of sugar in 1 kilogram of water. So in a situation like that, which is probably syrup, then you would say sugar is actually the solvent, even though water is the liquid in that example. And the reason why the sugar is the solvent is just because it's there in greater amount. It's twice as much sugar by mass as there is water present. We talked about solubility a lot in previous units. It's the amount of solute that will dissolve in a given amount of solvent. Now, for solutions, we have a variety of different units that we use to express. And the one we're most used to up to this point is molarity, which is moles per liter of solution. And this is probably the most common one we use in chemistry. Sometimes we use mass percent. Mass percent was often used to, so I think this was true. For a long time, there was a sort of point of pride, I guess, for Canadians that our beer is stronger than American beer. And the reason is that, and it wasn't true at all, and the reason was that Canadian beer is expressed, the alcohol percentage is expressed in volume percent, which means volume of ethanol over volume total. So it's the percentage of the volume which came from ethanol. We're using mass percent is what they used in the US to express percentage alcohol content for beer, which was grams of solute over grams of solution. And because ethanol has a density lower than 1, it's around 0.8, what that meant is that 1 milliliter of ethanol was a lot less than 1 gram. Yet the final solution that you have in there is mostly water, so the density is very close to 1. So if you have 5% beer in Canada by volume, sometimes we use this percent, volume over volume. That's equivalent for beer to about 4% mass over volume, which is mass percent here. So the equivalent beer in terms of alcohol content in the US would have a lower expressed alcohol percentage on the bottle than in Canada. And I believe some time ago they changed that to make them the same, because I think they realized that some people will purchase alcohol. The decision to purchase this versus that would depend on the alcohol content, people preferring the higher alcohol content, and so they would go for this one here. There's your little lesson today. There's so many beers available now, I don't think you could ever argue that Canadian beer is somehow stronger than US beer. Like, you can get beer anywhere from 0.5% in Canada up to probably 12% is maybe the highest I've seen, and it'd be just the same in the US. Mole fraction is another one, which is mole solute over total moles of solution. So this would be mole solute over moles of solvent plus moles of solute on the bottom. So that's another way we can do it. And the other one that I wanted to point out here is molality. We're going to be using this one more later on in this chapter. Molality is one you may not have heard of before because it's only used in specific situations. Molality is equal to the moles of solute over the kilograms of solvent. So molality and molarity are basically the same thing, same number, when the solvent is water and when the concentrations are small. But once the concentrations start to get large, molality starts to diverge from molarity for aqueous solutions. But the nice thing about it is that it uses moles of solute, just like we use for molarity, but instead of total solution, we just need to know how many kilograms of solvent we have to deal with in that sort of situation. This is helpful hints for interconverting, but we will look at some examples. The reason why molality is actually something that's worth using in certain cases is because molarity actually changes in a solution as you increase or decrease the temperature of the solution. Because molarity, just we use M or sometimes the fancy M, is moles over volume of solution. If you take a solution and you increase the temperature, that will expand the solution. The volume will change without changing the number of moles. So the molarity actually goes down in a solution when you heat it up. When you cool down a solution and it contracts, that causes the molarity to go up. So molarity is actually not independent of temperature. It will fluctuate slightly depending on what the temperature is, or pressure if it's at all compressible solution. Where molality, because it's moles per kilogram of solvent, mass does not change with temperature and mass does not change with pressure. So molality is a constant no matter the temperature and pressure that solution is under. So in conditions where that matters, it's better to use molality as a concentration unit, even though almost always we're using molarity in what we're doing here. And that's because whenever we're doing scientific experiments, especially in chemistry, what we really like to do is only manipulate one variable at a time. And for that reason, we like to perform reactions under constant conditions of constant pressure and constant temperature, in which case molarity doesn't really fluctuate under those conditions. Great. So let's do an example where we have to convert between molarity and molality. And I want to bring up my slide where I have my answers. Not because I don't know how to do this. I do know how to do this. It's because the numbers are already calculated out for me once I find this. Okay, so here's how we do a problem like this. We have, we're going to assume that this is an aqueous solution, by the way. So we have a solute, which is ethanol, and then the solvent is going to be water. It says, what is the molality of a solution that is 5.86 molar ethanol, whose density is 0.927 grams per mil? So what we can do in a situation like this is just assume some amount of solvent, assume some amount of solution. So if we just say, okay, let's pretend we have 1 liter of this solution, then what we can do is calculate out how many moles and how many grams we have of ethanol, and how many moles and how many grams we have of water. Great, so let's say we're going to assume 1 liter. That means in this solution we have 5.86 moles of ethanol, because we have 5.86 moles per liter and we have 1 liter. Also, we can assume that the total mass of this solution is 927 grams. Because we know the density, and we said we have 1 liter. So times it by 1,000 mils, and you have 927 grams. So you can see where we're going. We know what the total mass is. We know what the moles of solute is, and we can convert our moles of solute into grams of solute. So our mass of ethanol equals moles times molar mass. I guess, yeah, our fancy M is molar mass, not molarity, as I indicated over there. And so our moles is 5.86. Our molar mass of ethanol is 46.07 grams per mole. And that is going to be equal 270 grams. Okay. So we have our mass of solute, our mass of solvent is going to be equal to total mass minus mass of solute. 927 grams minus 270 grams equals 657 grams. Did that very quick in my head, right? Sure. For molality, we need everything in kilograms. So let's just right away change that to 0.657 kilograms. So that's our mass of solvent. And in fact, I said up front that this was aqueous. It actually doesn't have to be aqueous. Our value we calculate, like we're never going to bring in water, it's molar mass or anything like that. All we need to know is the mass of the solvent, whatever it is. And it's 0.657 kilograms. Okay, so now what we need to know is the molality, which we usually use confusingly a small m to indicate, but rather than just a small m, which we usually use for mass, we use a small m that's sort of cursive. So we have too many symbols now with m's, but live with it, I guess. How people do it. This is going to be moles of solute over kilograms of solvent equals our moles in this 1 liter situation is 5.86 moles over our kilogram of solvent, which is 0.657 kg, and that equals 8.92 units of molal, which we actually also use this italicized M. So that's the concentration in molality, which is actually pretty significantly different from its concentration in molarity. So if you were to take these two solutions and dilute them, eventually those two numbers would get closer and closer together. And of course, eventually at very dilute concentrations, they are effectively the same measure. When water is your solvent, I ought to say. Okay, so hopefully that's cool. Just assume 1 liter solution. You can assume any amount you want. You can assume 1 mil or 10 mils or whatever. Just the math is easier if you assume 1 liter, because you don't have to do any conversion to get the number of moles. But do it the way you want. It all works. In terms of solubility, and I'm sure you've heard this before in the previous unit, probably some other places as well, we have kind of one simple rule, like dissolves like. And what we really mean by this is substances with similar types of intermolecular forces will likely be soluble within each other. So if you have two substances that both exhibit hydrogen bonding, they're likely to be quite soluble in each other. Whereas things that are both, say, nonpolar are more likely to dissolve in each other in that situation. We actually have a way of measuring polarity when it comes to solubility called, basically the way you do this is you take a container and you fill it with water and octanol. Which has 8 carbons, 4, 5, 6, 7, 8, with an OH on the end, which is quite nonpolar. It will form a separate phase from water, and you'll have the two different phases. And you can put a substance in this mixture, stir it all up, and see what percentage of that compound dissolves in the octanol phase versus the water phase. So it's sometimes we call these partition coefficients. It's tells you how much it prefers to be in the polar water phase or the nonpolar octanol phase. Yeah, we know this. So in thermodynamics, if you go down at a thermodynamic level and you're looking at these interactions, the reason for this, there's actually a couple of different factors we have to worry about. One is we have to look at the strength of the solvent-solvent interactions, because solvent wants to be with solvent, because by definition, solvent molecules have the exact same types of intermolecular forces. So they have certain forces holding those molecules together that if you dissolve something, you can think of as inserting a solute molecule in between two molecules of solvent. So in order to dissolve something, you're going to have to break solvent-solvent intermolecular forces. You also have to break solvent-solute intermolecular forces as well, because you break the solute apart and disperse it into your solution. And that costs money. Not costs money, it costs energy. Energy's money. Why don't we call it money? Every time you break a bond of any type, whether it's an intermolecular force or a covalent bond or an ionic bond, breaking bonds always costs energy. Making bonds always releases energy. So these solvent-solvent interactions and solute-solute interactions that we're breaking are offset by the formation of solute-solvent interactions, which are these ones here. So energetically, whether this is a favorable process to dissolve something depends on the relative strength of the solvent-solvent and solute-solute interactions versus the solvent-solute interactions. Okay, so here's sort of our simple rule of thumb. If the solvent-solute interactions are stronger than the solvent-solvent and solute-solute, the solution will form. If they're equivalent, solution will form. And if they're weaker, the solution may or may not form. More likely to not form the weaker these solvent-solute interactions are. So the factor that I haven't mentioned yet is entropy. That forming a solution is always entropically favorable. So in this situation where, you know, the strength of the interactions isn't really changing when you form a solution, formation of the solution happens anyway, and that is driven by an increase in entropy. This, you know, you can almost say like this is delta H is negative. Delta S for all of these is going to be positive. This delta H is 0. This is delta H equals positive. So even though delta H is working against you in this final column here, it can still happen because that can still be entropically driven, right? The entropy part can overwhelm the strength of the interactions. This is all the same stuff I just said. Okay, so this is just a very quick reminder of the types of intermolecular forces we're dealing with. We have ion-ion, we have ion-dipole. Hydrogen bonding, very strong type of dipole-dipole. There are some subtleties that make hydrogen bonding different from dipole-dipole, which we'll talk about in the organic chapter, I think. We have dipole-dipole, induced dipole ion. So induced dipole, sometimes we call collectively these ones dispersion forces. These involve nonpolar molecules that have a temporary dipole, induced dipole, instantaneous dipole. So hopefully you remember your intermolecular forces. I believe that was one of the final chapters that you would have done before Christmas. You still have to know how to do those and apply them and recognize where they exist. So in terms of solvents that we commonly use, we have common ones that are polar here. We have water, acetone, methanol, ethanol. You can see these three all exhibit hydrogen bonding. So this makes them quite polar. And then we have on the other side a bunch of solvents that we call nonpolar. So this is like hexane, which is just like carbon and hydrogen, no bond dipoles, no electronegative atoms. Diethyl ether, very weakly polar. Toluene has a structure, it's like benzene. with a methyl group on it, CH3. Carbon tetrachloride, CCl4, symmetrical. It's funny that this is on a list of common nonpolar solvents because it's totally not common at all anymore. It used to be really common, but it got banned in 1998 by the Montreal Protocol because it's a really nasty not greenhouse gas, ozone depleter, because it can get up into the stratosphere, make chlorine radicals, and destroy the ozone layer. And so for that reason, tetrachloride is something we don't use anymore. We use it in very small amounts. It's become extremely expensive. So I found it was from the 80s. It was a receipt that was in some old drawer somewhere for an order of carbon tetrachloride, and it was a 20-liter drum. In the 80s was like $6. And now, if you want to buy like 100 mils, it's like $500. And that money is not because this is expensive or difficult to produce. It's tax. They tax the hell out of this stuff to dissuade people from using it because it's a banned material. Banned meaning it's not as illegal to use it. It means it's extremely highly regulated and taxed and priced. Kind of like alcohol. Alcohol is not a banned substance, it's a heavily regulated substance. And there's a lot of tax if you buy alcohol or cigarettes or anything like that. So there's certain reactions in certain situations where you need carbon tetrachloride. And actually we have in our department probably around 10 liters of carbon tetrachloride that it's a leftover from the 80s. And it's like very like closely guarded because it's necessary in certain situations and you got to be very careful with it. So every time we use, let's say we use 50 mils for some reaction, you would distill it out of the reaction when you were done and then put it back in the bottle because you can't just lose 50 mils. Partly for environmental reasons, and of course, partly because it's very difficult to repurchase if you ever need it again. So yeah, we do have certain substances that are like that. So not so common anymore. Sorry, carbon tetrachloride. You've been demoted. All right, so let's do this example and then call her quits for today. It says, predict the relative solubilities in the following cases. We have bromine, Br2, which has the Lewis structure like this. It's nonpolar. Benzene. By the way, when you guys did Lewis structures, did you look at these kind of skeletal representations of molecules last semester? Ever seen that before? This is a shorthand version, and maybe we'll get into that when we do the organic chapter next. That's like carbon, 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 hydrogen, hydrogen, hydrogen. This is benzene. This is a shorthand version of benzene. But again, it's just a hydrocarbon. There's no electronegative atoms. Carbon and hydrogen don't have very different electronegativities. That's nonpolar as well. So we would say that bromine should be very soluble in benzene and not so soluble in water, okay? Because water is very polar. So because Br2 is nonpolar, you don't expect great solubility there. It turns out bromine is actually somewhat soluble in water. And the reason is that it's very what we call polarizable, meaning that induced dipoles are easy to form in Br2. So it can be temporarily polar and still dissolve in water. KCl is an ionic salt, right? It's a crystal lattice. And for that reason, it's only going to dissolve in something like water or some other very polar liquid that can have very strong ion dipole intermolecular forces. So it's not going to dissolve in a nonpolar liquid like carbon tetrachloride, but maybe ammonia, because ammonia is quite polar. It's got hydrogen bonding because it's got NHs. And it's got a dipole, it looks like that. So it'll be pretty soluble in ammonia, not at all in carbon tetrachloride. Next, we have formaldehyde in carbon disulfide and in water. So formaldehyde has this structure. It's quite strongly polar. It will dissolve actually very well in water. And when you dissolve formaldehyde in water, you get a solution called formalin. And actually, in that case, the water actually reacts with the formaldehyde to make something we call an acetal. Don't have to worry about that now. Carbon disulfide basically has the same structure as carbon dioxide. It's a nonpolar liquid. So we would expect formaldehyde to be less soluble in carbon disulfide. But what we find actually is that small molecules like formaldehyde typically dissolve pretty well in many different things. So this is kind of a bad question, I think, number C, part C, because formaldehyde, I think, will dissolve to an appreciable extent in almost anything. It's not ultrapolar. It's polar enough to dissolve well in polar solvents, but it's also nonpolar enough to dissolve in nonpolar solvents. The other thing formaldehyde will do, if it's not in water and forming something called formalin, it will actually react with itself and make something called paraformaldehyde, which is a solid polymer. You know, it forms a big long chain of CH2O, CH2O, which makes it into like a white insoluble powder, and that won't dissolve in any of these things. So formaldehyde's a bad example, but the other ones are good examples. Salts, only in polar liquids. Nonpolar things, typically only in nonpolar liquids themselves. Great. So let's stop here. There's a homework version of this, which you can try out yourself. And then we're going to go into gas solubility in liquids too. Great. So thank you very much. Keep your eyes peeled for emails from me regarding the next assignment. And I am planning this morning to post the grades as well for the oral presentations. All of them went pretty well. So great. So have a good day, everyone.